We're going to start off with defining a random variable. It's going to be a term that you hear a lot of. Its formal definition is simply a variable whose outcome is determined by chance. Um, Anything that is a variable whose outcome is determined by chance. Variable, let's just start off from right off the bat here, making sure we understand what that means. A variable is just something that has a different value for different people in uh, sample or a population, doesn't matter. A variable could be hair color. It could be score on an SAT. It could be just any thing that your piece of information, any piece of data that you're collecting on your subjects. Again, sample or population doesn't matter. A random variable is a variable whose outcome is determined by chance. Your SAT score is not determined by chance, so it's not necessarily random. However, if I randomly select a student and want to know their SAT score, then that's determined by chance because who I picked was by chance, right? So any variable whose outcome is determined by chance, whether that's because I randomly chose a person or because I have a random event, like flipping a coin. Um, the last part of this definition links to what we talked about in chapter 3. It gets a little bit weird, but it's really important that you grasp this. It defines a numerical quantity to each outcome in the sample space. So outcome and sample space terms we talked about last chapter. It basically is going to help translate words to numbers. Okay, it's an easy way to think about that. We're going to translate words to numbers. Remember, we talked about the outcomes before of flipping two coins. We said, well, we have heads, 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 tails, tails, heads, tails, tails. Those are words. We're in a math class. We want numbers. A random variable is going to define a numerical quantity for each of those outcomes. Now, how we define it is up to us. We can define it however we want. Okay. Um, I can choose to say I'm going to define numerically how many heads I get into coin flips because that makes the words turn into numbers. So if I were to do that, I would say heads heads maps to the number 2 because I've defined the random variable to be how many heads I get. Then heads tails and tails heads both map to the number 1 and tails tails maps to the number 0. I could have flipped that and said how many tails I get. It's fine. It's irrelevant, right? It's a simple mapping. It's not anything overly complex. It's just saying how do we get the words and the outcomes to numbers? Okay. Now variables are usually defined with letters. So I have some notation here for us. Now it's important to note I'm not going to grade you on capital lowercase. I will grade you on making sure you know the symbols that we covered back in chapter 2. And we talked about that then, but the X bar, the mu, lowercase n, capital N, sigma, sigma squared, S squared. Those symbols have specific meanings that are very important, and you will be tested over your knowledge of those. This is just so you understand what I'm writing, but it's not super important for you to be tested over. I just want you to be able to follow along. So a capital letter random variable is just a generic random variable. I haven't observed it. I'm just talking about it. And a lowercase random variable is going to be a realization, something that's already happened. So if the random variable capital X represents the number of free throws someone makes in 10 attempts, I could say lowercase x could be all the different possibilities, say 6 free throws, 5 free throws, whatever. So in that case, I would say let capital X be the number of free throws someone makes out of 10 attempts. And then we're going to build a table later on, and we're going to say, oh, well, lowercase x could be 0, could be 1, could be 2, etc. What all the values that lowercase x could take, because lowercase x is the potential realizations of those, whereas capital X is the generic like definition of what random variable we're talking about. A probability distribution is a description that gives the probability for every possible value of a random variable. And by description, we mean table, equation, graph. When we get to chapter 6, It'll look a lot like a graph in chapter 4a here. We'll be mostly working with tables. In chapter 4b, we will shift to looking at equations. When we say probability distribution, it could mean any of them. We just are going to have different forms depending on what we're dealing with. If we get more complex in the statistics, we could utilize all three of them for any single problem, depending on if the problem allows us, at minimum two. And so what we mean by this is just we have to describe what the probabilities are. So probability distribution, just from the English sense of the word, right? How are the probabilities distributed? What do they look like? Okay, what values could they take? And so we say every possible value of the random variable. Think back to the idea of sample space, which lists out all of my possible outcomes. Now, when we think about random variable, we talked about in the last slide, maps those outcomes to numbers for every possibility that I have in the sample space. So a lot happening. You may need to go back and rewatch some different things. You may need to watch this multiple times, lots of new terms. What we're talking about here is all of those words that we have as our outcomes. All of them are in our sample space. The sample space is every possible option that is out there. And then we're going to map all of those to numbers, and then we're going to say, now we have a collection of numbers. That's the random variable, and all of those numbers now need to also go with a probability. So we've gone from words to numbers. That's just events, right? Remember we say the capital letter X equals 2. That's just saying I got 2 heads when I flipped the coin 2 times, or I made 2 free throws out of 10, right? So the X equals 2 part, that's just the events themselves. A probability distribution says, but that 2 needs to be paired with a probability. And all of the numbers of the random variable that they could be, doesn't matter how many there are, but every single one of them needs to have a probability that goes with it, because we can say how likely these things are. Now we have here, we call a probability distribution for a discrete random variable. In chapter 4, we're dealing with discrete variables. Remember back from chapter 1, discrete variables are those that have gaps. We call a probability distribution for a discrete variable a PMF. You don't need to memorize that. It's just here because I'm going to have to call it that later. Don't worry about memorizing that. And some properties. First off, we notate this probability distribution as f of x. Think back to Algebra 1, Algebra 2, back in whenever you took this, college algebra, doesn't matter. F of x is function of x. If you were to plot it, it would be equivalent to the y-axis, right? We're going to call our probability distributions in discrete variables, we're going to call them f of x. And note that f of x is equal, and this is where the capital lowercase thing comes in, equal to the probability that capital X equals lowercase x. Remember, lowercase x is going to be replaced with a number that's a possibility of a realization. So what we're saying is f of 4 is the probability that x equals 4. You need to know that those are synonymous. Put a star by that, highlight that. You need to know that. I'm going to use this later on, and you're going to have to pause videos and you're going to say, where did that come from? And it's going to be right here. I'm going to say, I highlighted this. I talked about this so that you know this, because I don't want you to get lost later, okay? Later on, we're going to say, what's the probability that x equals 4? And I need to say, that's f of 4. If I have a function, I can just go, boom, f of 4. All right, because that's what probability x equals that number is. That's f of that number. Okay, those are synonymous ideas. Every f of x has to be between 0 and 1. Notice those are inclusive. I have the or equal to there. That should make sense to you because f of x is a probability, right? Is in math is equals. So f of x is this is a probability, right? So because this is a probability, my probability has to be between 0 and 1. We covered that last chapter. So that should make sense to you. F of x equals 0 for every x. That is not possible. Now, there's a lot of eloquent ways to describe this and fancy terms you may see depending on what other resources you may look at. It's just easy for me to think about it. If it's not possible, then f of x equals 0. That should make sense, right? Because again, f of x is a probability. So if I'm talking about the number of heads I get when I flip 2 coins, f of 0.5 is impossible. I can't get half of a head. So any event that's impossible, its probability is equal to 0, right? Or f of 3 is equal to 0 in that scenario, because if I flip a coin twice, I cannot get 3 heads. I could max out at 2. My options are 0, 1, and 2, and in theory, this probability distribution would map out a probability for 0, 1, and 2. Everything else, f of x is 0, because every other value is not possible. And the last one, the sum of all of the probabilities must be 1. Make sure you know that last one. Make sure you know that last one and this concept right here that f of x equals the probability x equals x. These apply to probability distributions for discrete random variables. We're going to get to continuous random variables, and we're going to have some different things to contrast this with. Okay, remember I talked about discrete and continuous being two different types of data. They have two different ways they operate. That's what we're going to stress here in chapters 4 versus when we get to the brief time we're going to spend with 5 and 6. They have different things that are happening. So in chapter 4 with discrete variables, f of x is a probability, and the sum of all those probabilities, the sum of all of the f of x's, will add up to 1. Okay, those are things that we need to know, and we need to know that they apply specifically to discrete random variables, because those will not be true when we get to continuous. Now we shift into 4.2, and we're going to talk about means and standard deviations. Remember, we talked in chapter 2 about how to find the mean and the standard deviation of a data set. And now we're going to talk about how to find the mean and the standard deviation of a variable. Now, what I want to make sure you understand right off the bat is that when we are dealing with discrete variables, and this part will apply to continuous as well, notice that we're talking about a probability distribution. Probability. We said from chapter 3, we learned that probability is a long-term relative frequency. Remember, we said as if we had all of them, as if we knew the truth, as if we had an infinite sample size. Those are all population ideas. And so when we talk about a mean and a standard deviation in this context, remember we said every time we find a mean or a standard deviation, we can always say, where did it come from? Here, this is a population. Why is that? Because let's think about this. If it's a random variable and we're defining a probability, what we're saying is, what are the odds that this happens out of an infinite scale, right? What if I knew everything? What if I had every single person? What's its probability? What's its long term, right? Again, these all ideas align with a population. So we're finding a population mean and a population standard deviation because these are random variables that are, in theory, what would happen if I had all of them.